A type of series that will be your friend throughout a Calculus 3 course is the geometric series. It's very simple, and contrary to most other series, you can find its sum whenever it does converge. So it is worth keeping it close as a reference. You can compare it to other series to determine if the other one converges or diverges. So this is the first one that we're going to treat formally here, rather than just guessing based on tables or patterns that we see on the sequence of partial sums. So what this is saying, and this is what you have to write down, that the geometric series has this general form, and that it will converge whenever R, the ratio of the geometric series, is less than 1 in absolute value. So this, and that it converges to this. And in other cases, if R is 1 or greater in absolute value, it will diverge. Okay? So let me explain what this is saying. If you saw my video on geometric series, you know that on geometric sequences, you know that a geometric sequence is just a list of numbers in which every number is multiplied by a certain common ratio to find the next number on the list on the sequence. So if you have something like 1, maybe starting with a 1 like this, or a 1/3, and then a 1/9, and then a 1/27, and so on, every time you multiply a term by 1/3, so this is a geometric sequence, just a list of numbers. And if you want to find the geometric series, that will be the sum of those guys. Okay? Adding those guys is what the geometric series means, and we actually write it like this. Actually, what I wrote here is not correct. Take a look. Because if I plug in 1, this gives me 1/3 to the power 1. The first term here would be 1. So would be 1/3 the way that I wrote, but I want it to be 1. So I have to fix this to make it a 0, right? Or I have to fix, if I really want to start at 1, I have to fix the power of 1/3 and write n minus 1 here at the power, because then when I plug in 1, I end up starting at no r's, right? Just 1. So you can see why this is how it is. And the formula really can be thought of as, if you want, the top being the first term of the sequence. Doesn't matter where it starts. And the bottom being 1 minus the ratio. Because sometimes if your geometric sequence will start at some higher number, like a 19 or something, as long as you can identify that it's geometric, you can figure out what's the first term is by just plugging the first number you're told to plug in, and that formula will work. So let me give you a proof of this formula. I really like this proof. I think it's pretty clever. So let's write the sequence of partial sums. Sn, it will be a1 plus a2 plus a3 plus all the way to an, right? So that's what the sequence of partial sums is, a finite sum. But if you remember that the series is geometric, when I plug in n equals 1, I get r to the power 0. So there's no r's in this, but then there's an r in here, there's r squared, and then there's an r cubed, and so on. The last term being a r to the power n minus 1. So that's an equation that I'll save, the second equation. I want to find a formula for this. So the very clever move to get this formula, and this is the proof for this formula, is multiplying the equation by r. So if I multiply this equation by r on the left, I get r times Sn, and on the right I get ar squared. So each term gets an additional r. like this. Each term gets an additional r. Okay, let me move this example further down. So take a look at what I did, see if you believe me. Multiplying by r on both sides give me this. And now what I do is I simply subtract these two equations. So this equation right here, and from this I subtract this. And then we calculate it together. So on the left I simply get Sn minus r times Sn. Okay, on the left it's pretty simple. But on the right, here's what happens. When I subtract, these cancel. And these cancel. And these cancel. This is going to cancel with whatever comes after. And this one is going to cancel with whatever came before. If you know, the powers of r are growing, right? 1, 2, 3, 4. If it got to n here, that means the previous term had a power n minus 1, which is the same as this. So it does cancel with this. So the only terms that are left are a and a r to the power n. So now practically most of the work is done because Sn equals, so if I factor Sn from the left side, I get Sn times 1 minus r, and then factor a, I get a times 1 plus r to the power n. And finally I get Sn equals a 1 plus r to the, I believe there's a minus in here that I missed because I'm subtracting, right? So this here should be a negative. Let me fix that in red. But then I get to divide the 1 minus r that was dividing before. And then you get this. This is the formula for the sequence of partial sums of a geometric series. I think it's worth memorizing or even remembering how to prove it. It's not super hard. Just one trick that you need to use. And the geometric sequence is common enough that remembering this trick is worth it. Now, how do I make it a series, right? Now I have two cases. If if absolute value of r is less than 1, that means r is a decimal, like a 0.8 or 0.7. The more times I multiply r by itself, the smaller r becomes. So the limit when n goes to infinity of r to the power n is 0. So imagine you're multiplying 0.5 times 0.5 times 0.5 a bunch of times. The more times you do that, the closer that gets to 0. And if absolute value of r is 1 or more, then that won't happen. Okay. Which will make the limit. So let me actually divide this into a few cases. If it's greater than 1, then this limit is clearly infinity. And so the series will diverge. The case where r equals 1 is the case that we have to be more careful about. When r equals 1, that can't happen because the bottom of the fraction is 1 minus r. So that is not something that we can handle. So the series will diverge here as well. You can factor the top and cancel things out to see that. And when r equals negative 1, then this is going to be oscillating between -1 and 1, -1 and 1. So this will sometimes be 0, sometimes be something else. And so Sn will diverge. You can think as well about the case r equals 1. If you go back originally to the series, you're multiplying each term by r, but if r is 1, you're not changing anything about those terms. So if r is 1, Sn equals a plus a plus a plus a all the time. So unless a equals 0, this will diverge. Because if you're adding a positive number over and over, then you get infinity. If you add a negative number, you get negative infinity. So this formula that I proved, that I just wrote with you, only converges, only has a limit, a nice behaved limit, nicely behaved limit when r is less than 1 in absolute values. And when it does, this thing goes to 0. So just get a times 1 at the top, which is a, divided by 1 minus r, which is exactly what this said at the beginning. So I hope this proof was enough to clarify what's going on and the reasons why this is what it is. Let's do a couple of examples, because from now on, as soon as you're able to identify that your series is geometric, you don't need to be playing with the sequence of partial sums anymore. You can immediately tell somebody what's the ratio and determine from that whether the series converges and diverges. And as a plus, you can also find its sum based on this formula. So as long as it converges. So let's talk about these examples here. This one, I can see that it has this format. This is the same as 1 2/3 to the power n. So this is geometric. The ratio is 2/3, so it converges. And furthermore, I can find the sum. The sum is the first term. So the first term is obtained when I plug in this first term divided by 1 minus ratio. So whenever I plug in n equals 1, that's my first term. So that will be 2/3 on the top of the fraction, 1 minus 2/3. So it will be 2/3 divided by 1/3. So it will be 2/3 times 3/2. So the sum is actually equal to 2. Yes. So this first series converges. It's geometric with ratio 2/3. And it does add up to 2. So that's a really powerful set of statements there about a series. Not always that you can do this. Let me copy this because I thought I'd have space to do all of them at once. So let's do 2. Let's do B actually. So you see that B is also geometric. Let's do B. This one here is geometric. You can see that. The ratio of this is 0.8. You see, because the power of 0.8 is n, then that will be the ratio of my geometric series, which means because the ratio is less than 1, the series converges. And the sum is going to be again, first term one minus ratio. First term is obtained when I plug in n, the first value for n. And you can see over here on the left that the first value for n is 2. So the first term is going to be 3 times 0.8 squared divided by 1 minus the ratio, like this. Okay, so we're going to find this as being 3 times, so I'm gonna make this a fraction because I think it's gonna be easier for me to calculate. I have my calculator here on me, but I want to show you that you don't need it. for this problem at the very least. So 0.8 is 8 over 10, which is 4 over 5. So when I square this, (16 over 25) is what I get. And then at the bottom, you do 1 minus 4/5, which is 1/5. So this is 3 times 16 over 25 times 5 over 1. These cancel to get a 5 here, and then you get 3 times 16 over 5. Can I make this a little better? I don't think so. I think this is fine. You have 48 over 5. You can make it a decimal if you want. It's not too bad, but usually when you don't have a calculator, a fraction as an answer is acceptable. But if you really want to make it a decimal, you can multiply by 20, top and bottom, to get at the bottom 100, which is what makes it easier and what prompts me to multiply by 20. And the top this time, multiplying by 20, is just doubling and adding a 0. So 48 times 2 is going to be 96 with an extra 0. So this is going to add all the way to 9.6. Okay, so the more numbers of these you add, the closer you get to 9.6. Now this one here, let me go back to the rest of the examples. This one, the ratio, this is geometric. The ratio is 5 over 4 instead of 4 over 5. So it's a bigger number than 1. Right? It's a number that's greater than 1. So this diverges, and there's nothing for me to find. It diverges actually to positive infinity because I'm adding numbers that are bigger and bigger all the time, but I don't have to say that. And so the same happens with D. Even though the ratio is just a tiny bit bigger than 1, just a tiny bit bigger, then it still diverges because the numbers you're adding are getting bigger and bigger and bigger all the time. Just imagine you increase by 0.1%, maybe 0.01% every time, and the numbers are getting bigger and bigger and bigger. If you wait long enough, you'll be adding very huge numbers if you increase something by 0.01% multiple times. But this last one, which is kind of interesting, this is also geometric. The ratio now is less than 1. So believe it or not, this converges. Even though it's very close, these two, D and E, are very close at the beginning, this one is going to shrink quick enough that the numbers, when I add them all together, are going to add to a finite number, and this one is not going to shrink. It's going to increase, and the numbers are going to get extremely, extremely large. And this one, the sum, is going to be something I can find. I'm able to find this. It will be the first term, 1 minus the ratio. So the first term, I obtained by plugging in 0. So that will be 0.999 to the power 0. And then 1 minus 0.999. So any number, non-zero number to the power 0 equals 1 at the top of the fraction. And then this minus 1 minus 0.999 will be 0.001, like this. And so this will be dividing something 1 by this. Whenever you're in doubt, you can always just do this. Just multiply by however many. Multiply by however many decimal points you want to move. 1 with however many zeros as decimal points, decimal places you want to move the decimal point. So if you do that, you'll end up with 1,000 over 1. So this adds to 1,000. Adding infinitely many of those powers of 0.999 adds to 1,000. It's a finite sum, right? So it's an infinite series that adds to a finite sum, and it so converges. One thing to be careful about is the following. Sometimes you're going to encounter an example. I just thought of this, so it's not typed up. You're going to encounter something like this. Let's say n from 4 to infinity of 7.2 to n plus 1, like this. So how can I see whether or not this is geometric and what's the ratio of this? Look, it looks geometric, but the power isn't correct. A person could look at this and think, okay, the ratio is 0.2, but it really isn't. The ratio here, if you play with this a little bit, you can say this is 0.2 squared to the power n times an extra 0.2, like this, to the power 1. You see, this first two together, this is a power of a power, so you multiply the powers, the exponents, to get the 2n. So this one is the same as 0.2 to the power 2n. This one is 0.2 to the power 2n without the 7. And this one is just 0.2 to the power 1. And when you multiply these two together, you add the powers to get you back to this. So if you were to play with this one more equation, this will be 0.2 squared. So 0.2 squared will be a 0.04. And then times 7, right? So maybe I'll do this. Okay, let me be very clear. I'll combine this with this because there are no n's in these two. So I'll do 7 times 0.2. So that will be 0.14, right? No, 1.4 should be. Right, that's right, yeah? Yeah, that's right. Double it, divide by 10. But then 0.2 squared to the power n, which is 0.04. So now that I've done this, I now can see that the ratio is r equals 0.04. Okay? So just got to be careful here with finding the sum. And so the sum of this will be, again, first term, 1 minus ratio. So it will be, you can go back to either formula, plug in the first value of n that you're given. I'm going to plug in n equals 4 into the original formula. So I'll get 7.2 to the power 2 times 4 plus 1. At the bottom, 1 minus 0.04. So I can use my calculator to do this. Right, so you can see I have a finite calculation to do. The series still converges, but the sum, the ratio is different than one would originally have thought at, when looking at this problem. So let me check what the sum here equals. And divide by 0.96. It's a very, very small number, so I'm not going to bother writing it down because the top of the fraction is very, very small. Raising 0.2 to the power 9 gets smaller and smaller, so I'm not going to bother writing it down. I'm going to leave it as is. Maybe we can find a way to write it as a fraction if necessary. But in any case, I just wanted to show you this example.